Hey everybody, it's Mrs. Dinkelman, and we're moving on to Unit 11 where we're creating polynomials and then seeing where those polynomials might converge or where they would match up on a graph if we look at it visually. So I'm going to talk a little bit visually and a little bit algebraically, just kind of depending on which way makes the most sense for your brain. So historically, mathematicians were trying to figure out if there were ways to turn things into polynomials. So think about a graph of sine, for instance, with all its hills and valleys. Is it possible we could turn that into a polynomial or make a polynomial that matches that exactly? And the reason we might want to do that, there's a couple reasons. One is if I asked you to figure out what sine of 3 is, you would have to get to your calculator to find that. Well, historically, they didn't really have calculators that do that. There was a big, thick book that they had, and they would try to figure out what sine of certain things were. And then they would also use those trig identities. Well, with polynomials, the only operations you really need to be able to use are add, subtract, multiply, divide. Those are very easy to do by hand. Even though it might be tedious, it's still doable. So if you could turn that into a polynomial and plug a 3 into the x value, it would be a lot simpler. Also, as you know, derivatives and integrals of polynomials, a lot of times, they're a lot easier than looking at some of the others. So that was one of the reasons historically that, that mathematicians wanted to do that. My sense is that in your calculator, for instance, when you type in sine of 3, there's actually a polynomial because calculators they found are really easy to program that they can do add, subtract, multiply, and divide. So if they just plug that value into the polynomial, make sure that they have enough terms where you don't see an issue or a difference, then they're good to go with that programming. So that's what my sense is, that your calculator is not actually remembering what sine of 3 is, it's actually calculating what that polynomial with a 3 plugged in would be. Okay, so for us, and I just want to come down here and show you what the examples are going to look like. So algebraically, instead of thinking about how graphs match up, what we're looking at is what values can I plug in for x and make this series converge. Let's come look at this one. This one, to me, in my mind, well, even this one, pretty easy to decide that at 0, this is going to work because then everything else doesn't matter and I'm going to have 0 plus 0 plus 0 plus 0. So I know that plugging a 0 in would work, but are there more values for x that would work? That's kind of our algebraic question. Once we've done and found the interval here, we'll actually perhaps look at some functions. We'll see. Maybe this one down here we'll be able to look at and see what the thing would be. Okay, so there are really 3 options when we look for the interval of convergence. We're going to get 3 results. One is that the series only converges at one value. So maybe like in example 2, and I said 0 works, maybe that's the only value for x that would work. Number 2, the series could converge for everything. So back to that sine example. So if I have an infinite amount of terms, then that polynomial will match to sine all the time. So visually, that means those 2 graphs look exactly the same. Algebraically, it means I can plug any value in for x and it will work. It will converge, I should say. More than likely, this is the thing that's going to happen. Number 3, we get an interval. And that interval might be something like, well, from -3 to 3 is where we converge. So we'll kind of peek at an example at least, maybe that 3rd one. So finding that interval and radius of convergence on these examples, we are going to be best friends with the ratio test. That's going to be the easiest way. So notice here how we have this interval set up with the absolute values. So that's really going to help us, that ratio test. So I'll do a couple of examples and then you can give it a try as well. Okay, so remember with the ratio test, and again, to get full credit, and by the way, sometimes we revert back to k's or n's, so if you do n's because you're used to n's, I know I do that all the time, that's fine. So this is really x plus 2 to the k plus 1. Remember, we do the k plus 1 over the k's. Now I'm going to skip a step knowing that it's going to make me run out of space here. Okay. All right, so let's figure out what that looks like. Again, really just a reminder if I didn't say it specifically enough, really it's k plus 1 over k, but I've already flipped and multiplied this part. So again, a combination of what we do here, that's really a limit, and that's just a polynomial with degree 1 over a polynomial with degree 1. So that becomes a 1. Its limit is a 1. And then here, this is more an algebraic issue. If I have k of these and k plus 1 of these, then they're going to cancel each other out, and I'm just going to be left with one of those. So I think what I have here is the absolute value of x plus 2. I don't need the limit sign anymore because the limit is about k, and I do not have any k's left over here. So just a quick reminder for us to find that something converges on the ratio test, we have to have our limit be less than 1. And that's what we're looking for. We're only interested in where this thing is going to converge. So we're going to put, okay, we need this to be less than 1, and we're going to solve this inequality for x. Well, if you remember solving absolute value inequalities, if we have, this just reminds me of, it looks like a C value, so we're going to make what's called a conjunction with a negative on the other side, because remember with absolute values it's distance and negative doesn't really make a difference. So I think our interval is -3 is less than x is less than -1. Now here's the problem with this, and it's going to take a little bit of time. I might have to take up some space and erase here in a second. But remember that in the ratio test, if we get equals 1, that we have something that's inconclusive. So it may or may not converge, excuse me. So that means we're going to have to do a little work here to decide if these endpoints do work, because if we get an equals 1, it's possible that the thing still converges, but we don't know that looking at it like this. So I'm just going to kind of take up some space here. I'm going to see what happens when x is -3. So I'm literally going to take that -3 and I'm going to plug it into that original question. So I'm going to call that, let's see, -1 to the k over k. That's what it's going to look like. So I just stole that from here. It's just kind of hiding. Well, we know that that converges by the alternating series test. So depending on how much work we need to show, alternating series, and that's because limit as k approaches infinity of the non-alternating part is 0. Okay, so that means -3 is going to work. So I need to go make sure that I include -3. So let's check now -1. So if I plug in -1, let's see, this is going to become a +1 to the k and a k. So a +1 to the k, well, that's always just going to be a 1. So I really could just call this a 1 in the numerator. And now this is it's a harmonic series, so this diverges. So I should have written over here, this converges. This one diverges. So -1 is not, it's not going to work. So this really is the answer to my interval. And for the radius question, if they ask me about the radius, I'll just come over here, radius. So what I like to think about is if that's the diameter, that's my distance, really that distance is 2, so my radius is 1. And there's one other part that we could see here. As long as there's nothing in front of the x here, that's my radius. So I can see it there as well. Okay, so ratio test is our best friend. We figure out what we have. We always set that thing less than 1 to solve because that's the converging. And then we have to test the endpoints. And maybe it would be helpful to write what our steps are. I'm just going to erase here so that we can get to example 2, and then I'll also write some steps for what I think we should do. So if you want to insert those steps into your notes, then you'll have that available too. Okay, so what we did here was we did ratio test. Okay, 2, we set it less than 1 because that's converging and that's to solve. And then we have to check the endpoints. Okay, so let's do that same thing here with example 2. So limit as x approaches infinity, and let's see, we're going to have k plus 1, x to the k plus 1, k factorial, so k plus 1 factorial. We're going to have a little bit of work here to do, and again, I'm going to skip to this part. Okay, so let's see what we have left here. So this guy and this guy, their limit is 1. Okay, so we'll just say that's a 1. X to the k and x to the k plus 1, that's going to cancel, and we're just going to be left with x to the 1. So don't let me forget that there's an x to the 1. Maybe I should just insert it over here. I'm going to leave a spot for the limit just in case we still need it. x. Okay, and then remember with factorial, so this factorial is really like k times k minus 1 times k minus 2, all the way till we get to 1. And this one is really k plus 1 times k minus 1, all the way till we get to 1. So from k on, cancel. So let's see, I think this is what I have. I still have k, so I need my limit. And just by the way, the x doesn't matter here because it's not the variable I'm concerned with right now. I just have something bottom heavy, which is 0. Well, 0 is always less than 1. So that means that this thing is always going to converge. So if we wanted an interval for this one, we could say, always converges no matter what x, and our radius technically is infinite as well. So that's what it's going to look like if we end up with one of those other ones there. Okay. Now, just kind of a by the way, some power series are geometric. So we can choose to do this ratio test. So ratio test is like the quadratic formula to me. You can use it all the time, it always works, but sometimes factoring is just a lot simpler. So we're going to think the same thing here. We can use a ratio test every time, and if that's the way you want to do it, that's totally fine. But sometimes we can use geometric series. The nice thing about that is we do not have to test the endpoints, because if you remember with the geometric series, if our ratio is equal to 1, or absolute valued, then we get to say diverge. So we don't have to check endpoints if it's geometric. Remember, the quick way to tell if something is geometric is to just notice that the k's are only in the exponents. So if we look at example 1 and 2 up here, there were k's outside of just the exponent. Okay, so those are not geometric, but example 3, the k's are only in the exponent. So that means we can just say, and maybe it's worth rewriting this to say, oh, this is just the same as like 2x over 5 to the k. Okay, so we need that ratio, the absolute value of it, to be less than 1. And there's again, no question about the equal to 1. Equal to 1 is definitely a diverge. So now, if we write our conjunction and multiply, okay, then that's our interval of convergence. And again, we do not have to test the endpoints in that case. Again, this one, if we wanted the radius, I kind of think of the 0 being in the middle here. So our radius is really the 5/2. So it wasn't just this one, and that's because there's a coefficient. Another way to write this, by the way, equivalently, is to say a couple things. I could take the 2/5 out because it's positive, so it's not going to have any bearing on the x. And then I could have it look like this. There's our radius right there. So that's another way, is to kind of isolate that x. I don't mind just finding it after I've found the interval, though. It seems like it's not too terrible. I'm going to show you a visual when we get to creating the power series next, so just in the next section. So if you are hoping to look at a visual, I'm going to go ahead and do it on that one instead of this one. You might, by the way, if you want to right now, just on those interval of convergence ones, is to just kind of take a peek and see if there are any that are just strictly geometric. So I can see this number 3 here, ends are only in the exponent, so you can kind of just use that really short trick instead of having to do the ratio test on that. So that's kind of a good thing to do if you would like. Okay, now sometimes you'll be asked to find the interval of convergence for a derivative or an integral of a power series. So that's what this example is going to be. And just kind of a by the way, the interval should be the same for both. It's just whether the endpoints converge or diverge, that may differ. And just so you know, if you don't trust me, I really don't mind you testing every time. In fact, as a student, I did that. I was like, I don't know if I think that's going to happen. It turns out it worked out for me. But there's always good to have a little bit of, what's the word I'm looking for, to just kind of question me a little bit and make sure you believe that's true. So example 4 is not too terrible. It looks to me like it's going to be a geometric. So I'm not going to do that thing where I test the endpoints. I'm just going to say that I need the absolute value of x over 3 to be less than 1 and not test the endpoints, because geometric, we know that that's not going to be a problem. So my interval is going to be that. And Now let's go ahead and find f prime. So on f prime, what we're suddenly doing is treating x like it's a variable. And really probably this should say f prime of x so that we know that explicitly. So f prime of x is equal to, so what I know is anything without an x is a constant. So that 3 to the n is just a constant. It's really the x to the n that I have to take the derivative of. So that's what that's going to look like. Now again, I could do ratio tests, but what I'm telling you is I know that for the ratio test, I'm going to get the same interval. It's just that now that this is not geometric because of the n here, I want to see whether or not this thing is going to converge or diverge at the endpoints. So let's see what happens when we have x is -3 and when x is 3, and just see what we can do with this. Okay, so at -3, we're plugging this in for x here. So where we're going to have n over 3 to the n, and let's see, -3, and oops, that's an n, not an x. So, oh, I had that right. So -3 to the n minus 1. Okay, let's simplify that a little bit. So first of all, what I want to do is figure out whether this thing alternates, because I'd rather have the negative kind of like out on its own, so I know it's just the alternating part, and then I can separate it. So let's think about this. If, let's say, n is 2, for instance, then we know for sure that we're going to have a positive down here. That actually will always be a positive. This would be negative, or when n is 3. So I believe this does alternate. It makes sense to me. There's no negatives in there to cancel it out from alternating. So I'm just going to call it -1 to the n minus 1. Okay, so I've taken care of that negative part. There is an n on the top, and let's figure out what's going on with these 3's. So the 3 to the n and the 3 to the n would cancel, and then I'd have a 3 to the -1 left. Okay, so let's see what happens with that. Now this is alternating, but the limit is not 0. So this diverges by alternating series. Okay, all right, so we don't have to worry about the 3. So let's see what happens with x equals, sorry, that was -3, with 3. So basically, I think what we're going to get is this same thing, but we're not going to be alternating, which makes it almost even worse. Okay, so we're going to have an n over 3 to the n, and then a 3 to the n minus 1. So that simplifies down to just n over 3. And that diverges by nth term because the limit is not 0. Okay, so same as that interval. So let's go ahead and see what happens when we find the integral or the antiderivative of this, okay? Again, the x to the n is really, the x is the variable in this case as we're trying to figure it out. I'm going to label this as capital letter F. So, all right, so we have that 1 over 3 to the n, and what we're going to do is we're going to add 1 to the exponent and divide by our new exponent, and then we're going to see what happens. So let's see. Again, I think same interval. And then let's see, so when x is -3, we're going to have, all right, I'm just going to put this on the top, -3 to the n plus 1, and a 3 to the n, and then an n plus 1. So we want to have that same discussion about whether this does alternate, and I believe it does. There aren't any other negatives to cancel, so I'm just going to kind of factor out that extra -1 there. So that's -1 to the n plus 1. And then with the 3's, now that I've taken care of the negative, there's just an extra one on the top, so that's 3 over n plus 1. Now this one is alternating and the limit is 0, so this converges by the alternating series test. So let's see, converges, that was with -3, so we get to underline that one. Okay, what about +3? So really the only difference here should be that it doesn't alternate. So it's going to be 3 over n plus 1. Now really this is going to be like a comparison. If I have an n to the 1 on the bottom, really I'm going to compare it to 1 over n, which diverges. I'm not going to show my work too much here unless they really ask me to justify. So this diverges by, and I would just say comparison. And if I needed to justify and show my work, then I would definitely do that. Probably a limit comparison because that's the one that I like. Okay, so that's how we take the derivative and take the integral. and then also check to see if what the interval of convergence is. So next section, hopefully I will show you what it means to have an interval of convergence visually.